Hey guys, it's time for more AP Chemistry. This is podcast 12.4, where we will specifically look at the mechanisms of reactions. Reaction mechanisms are simply a method used to show the intermediate processes that occur during a reaction. So we want to be able to describe how the reaction occurs. We'll list the proposed changes that take place to the reactants as the products are being formed. Usually this is 2 or 3 chemical reactions that are referred to as intermediate reactions or elementary steps, intermediate reactions or elementary steps, and we show one on top of the other, like step 1 above step 2 and step 2 above step 3. So the problem is we could probably describe several different mechanisms, and we can propose a couple of different ways. How do we know which one is correct? Well, first of all, any mechanism that is valid must follow the rate law that we find experimentally to be true. And we also know that it must follow the stoichiometry of the overall reaction. So these are our 2 criteria that must be true in order for the mechanism to be the correct one. And of course, for each elementary step, there's an activation energy that must be overcome for each of the reactions in the mechanism. And the activation energy, of course, determines the rate. Which of these steps is going to be the fastest step depends on which one has the lowest activation energy, right? And the slowest step is the one that determines how fast the reaction can actually proceed. The Arrhenius equation gave us the ability to calculate the activation energy based on a comparison of temperature and rate law, where K determines the rate. Your slowest step, of course, is the rate determining step. That's the one that has the highest activation energy. Here's an example of a reaction where nitrogen dioxide combines with carbon monoxide. We've seen this example before. And the analysis of this reaction has detected the presence of this substance NO3, which is neither a reactant nor a product of this reaction. One explanation is that in the first step, the collision of 2 NO2 molecules results in the formation of this NO3 intermediate. And then in the next step, the NO3 is actually the particle that collides with carbon monoxide in order to form NO2 and CO2. So this is the proposed mechanism where one thing is formed in one step, then consumed in the very next step. So it doesn't linger around for very long. Remember that activated complex? This is kind of like an activated complex, only now it's an intermediate in the reaction because it actually exists long enough for us to measure its presence and detect that it's there. So that's what an intermediate is. Neither a reactant or a product, but it exists during the reaction because it's formed in one step and then later on used up in a different step. The molecularity is a way of describing the number of pieces that have to come together in order for each step to take place. So in each elementary step, the number of molecules that take part in the reaction determine the molecularity of that step. A unimolecular reaction is one in which only one molecule is involved. And of course, for a bimolecular reaction, you need 2 molecules that collide into one another. And termolecular involves 3 molecules. It would be pretty rare to have more than that because even a termolecular would be rare. It requires the simultaneous collision of 3 molecules all at the same time. So here's an example of another reaction. So we'll use these 2 elementary steps to construct the balanced equation, and we'll determine the molecularity of each step. So here's our step 1. Step 1 in this reaction is that NO2 has to collide with F2 to form NOF2 and oxygen atoms. So if we have a molecule of NO2 that collides with another molecule of F2, then this is bimolecular. The next step, step 2, has the collision of NO2 with that oxygen atom, NO. Again, we have two molecules that have to collide into each other, and so this step is also bimolecular. Oops. We still have to add these together, so let me clear my writing out of the way. The next part asks us to construct the balanced equation. So let's see what we get when we put these two reactions together. If I have NO2, I'm just adding these two equations in both, then I get NO2 plus F plus O. So that's all of my, F2, right? That's all of my reactants. And all of my products would give me this NOF2 plus O plus NO3. All right, now I'm going to cancel out the things that show up on the same, or on both sides, because that's how we add equations together. If they're on both sides, they get canceled out because it's formed here, then used up here. So my overall balanced equation shows 2 NO2s plus F2 yields NOF2 plus NO3. There's our balanced equation. And both of our elementary steps, or intermediate steps, were bimolecular. Let's look at molecularity and rate law. When you're given a rate law, you can determine the molecularity of that step. So for A to turn into products, if it's just one molecule, then we would write its rate as K times A. This is a unimolecular step. Yeah, can't spell. U-N-I, unimolecular. But suppose that we had to have two A molecules bump into each other. Then our rate law would look like Ka squared. This is bimolecular. What if we have this kind of reaction, 2A? Then we write the rate law this way. There's still two molecules colliding, and so it's bimolecular. What if we had to collide with a different type of molecule? A plus B? What do you think? When A has to collide with B, that's two molecules colliding. That one is a bimolecular step. Now we have two A's that have to collide with a B. You got it. 3 of them makes it termolecular. What if we write it this way, 2A plus B? Does that change anything? Nah, it's still the same as the step before. How about 3 different types of molecules? Then the rate law looks like this, and it's still a termolecular step. The rate determining step is going to be the slowest step. In any reaction mechanisms, each different elementary step occurs at a different rate. It's the slowest one, though, that determines the overall speed. So this is what's called the rate determining step for the reaction, and it's going to determine the overall rate at which the reaction can proceed. It's kind of like in a big line of traffic. If there's one car going slow, all the cars behind it have to go slow too. So what do we do in the rate law when we have an intermediate? We can't keep an intermediate in the rate law because there's no way you can measure its concentration for the rate law to be experimentally determined. So we use the reactants that form those intermediates if an intermediate is in our slowest step. So if the reactions are fast and irreversible, the concentration of the intermediate is based upon the reactions that form it. So we just look at the stoichiometry. If the intermediate is formed by a reversible reaction, then we set the rates equal to each other. Let me show you how we do this. So here's the reaction where we've got a mechanism provided. We know which step is the slowest step, and so now we have to write the rate law. So since the slow step is our rate determining step, then we'll start out by writing our rate law with the reactants of our slowest step. So I'm going to use the symbol K2 for reaction 2. The rate of reaction 2 is determined by the rate law constant times those reactants. These two things have to bump into each other. That's what the mechanism is saying, is that these two things have to bump into each other, and this is the one that's the slow step. But look, the N2O2 was formed in step 1, then used up in step 2. So this is our reaction intermediate. We won't be able to measure its actual concentration. Intermediate. How come I can't spell today? There. That's our reaction intermediate. So we can't measure its concentration. We have to go back to the reaction in which it was formed. So K1, my rate law constant for my first reaction, times NO to the second power, because we have to have two of these collide to form NO2, is going to give me the reverse of the formation of my intermediate, N2O2. So now, how do I write this rate law? I'm going to take K2 times my reversible reaction. We're just going to put one on top of the other. If they're equal, then I can put one on top of the other, and I haven't multiplied by anything, right? It's just multiplying by 1, because they're equal. So I have the concentration of NO squared times O2 squared. Why? Because this came from this. So I put one in the place of the other. So I get my overall rate law, K times NO squared times O2 to the first power. Suppose that we have intermediates formed in fast reactions. So I have this reaction, 2IBr breaks down into iodine and bromine. And my mechanism lists a fast step, a slow step, and another fast step. So what do we do to write the rate law? Well, first of all, we're going to start off by writing the rate law for the slow step. So I'm going to number my steps so that you can follow what I'm working on here. 1, 2, and step 3. The rate of my reaction is going to be equal to K times IBr times Br, because this is my slowest step. It's my rate determining step, so I take the collisions that need to take place for that step and put them into the rate law. But we've got a problem here, right? Do you see the intermediate? It's right here. Br is formed in step 1 and then used up in step 2, so we are not allowed to keep that in our rate law. But what we know is that the concentration, square brackets, the concentration of bromine atoms comes from, entirely from, the concentration of IBr molecules, right? And so in that case, I'm going to put this in the place of the Br. Since they're equal, then I can use substitution here. So my rate's going to be equal to K times IBr times, now I'm putting IBR in the place of BR. And we can rewrite this as IBR squared. Either way, it's a bimolecular rate law. And that's going to give us the rate. Now, of course, we'll test this out experimentally, and if this rate law does not match what the experimental data shows, then it's not a valid mechanism to propose these 3 steps. But this is what we get when we look at the steps and look at which one is the slow step. Then this is the rate law we get. We're going to compare this to actual experiments and see if our theory matches up with reality. If it doesn't, we have to adjust the theory. We don't get to adjust the data to our liking. We adjust the theory to fit what the data shows. Let's do this one more time. I think it's important for us to all be very clear on how this is done. Okay, so we have a longer example now. We have this reaction between NO and H2 that's believed to occur in a 3-step process. So here's step 1, step 2, and step 3. And the second step is our rate determining step. So part A asks us to write a balanced equation for the overall reaction. Okay, here's our 3 reactions. If I add them together, what do we get? Well, before I start adding, let me see what I can cancel. Here's an intermediate, N2O2, and then we formed N2O here and used it up over here, so that is also an intermediate. How about the water? Does the water get used up anywhere? Water's formed here, but it's still there in the end. So I guess we'll have to keep that water. All right, now I have 2 NOs plus 2 H2s. And what I get in the end is N2 and 2 H2Os. Well, let's check to see if this is indeed a balanced equation. 2 nitrogens and 2 nitrogens, 2 oxygens and 2 oxygens, 4 hydrogens and 4 hydrogens. Sure enough, that works out. Now this one right here was our rate determining step because it's our slow reaction. So we've answered part A by balancing the equation for the overall reaction. Now let's have a look at the question for part B. It says identify the intermediates in the reaction and justify your answer. So we would identify N2O and N2O2 as intermediates, and our justification is that they're formed in one step and consumed in the other. There we go. All right, let's look at part C. From this mechanism above, the student, A student, deduces that the rate law is K times the concentration of NO squared times the concentration of H2. The student then concludes that the reaction is third order. The mechanism involves the simultaneous collision of 2 NO molecules and an H2 molecule. And the question is, are conclusions 1 and 2 both correct? And explain our answer. Okay, so in the information of the problem, they tell us that the correct conclusion is that NO squared times H2 is the rate law. That's the correct rate law for this reaction. Let's see where that came from before we answer the rest of the question. You see this step, step 2, is our rate determining step, right? And for that to happen, we would need to have the collision of N2O N2O2 with H2. And that problem in that rate law is right here. N2O2 is an intermediate, so we don't get to list that in the actual rate law, but we come back here and see where did that form. N2O2, it formed as a result of the collision of the NO with another NO. And so we can say when two NOs collide, then we form N2O2. And so we can write that in the place of the N2O2, since we're not allowed to keep intermediates in our rate law. And then, of course, in the place of N2O2, we've written the NO squared, but we have to keep the H2 also. That's part of our slow step, right? So that's where this rate law comes from. That part of her conclusion, or his conclusion, was correct. The student then concludes that the reaction is third order. What do you think about that? Is this a third order reaction? Remember how we determine the order? We add up the exponents. We have something squared and something to the first power, so yes, this is a third order reaction. That's true. How about the second part of the conclusion? The mechanism involves the simultaneous collision of two NO molecules and an H2 molecule. Is that what our mechanism shows? Go back to your slow step. We have a star. The mechanism actually shows that the rate depends on the collision of N2O2 molecules with H2 molecules. And so I think that's where our student has gone astray. These two must collide, not two NO molecules. So now we have an explanation for our answers. The first conclusion was correct. The second conclusion was incorrect because that student was looking at the rate law, not the rate determining step. All right, well that's it for our podcast about mechanisms. We'll get to practice more in class together, and I'll see you next time.